Hi, everyone. Thank you for joining. It's my pleasure to welcome Dr. Nick Spies, Medical Director of Applied Artificial Intelligence at ARUP and Assistant Professor in Pathology at the University of Utah. Hi,
Thanks for
Nick.
having me.
Absolutely. Pleasure having you. Thank you for joining us today. And I want to start by saying, I'm sure you get this a lot. What a cool title. Medical Director of Applied Artificial Intelligence. I have to say, it's something we've all been hoping and waiting for, right? We've all seen how AI has taken over the world in the last couple of years. So I'm curious, for everybody who doesn't know, what does the Medical Director of Applied Artificial Intelligence do?
Yeah, I mean, it's a great question. It's something we're still trying to kind of actively figure out. Obviously there's a ton of enthusiasm and a ton of kind of potential for artificial intelligence-based solutions to really help us do what we do in the laboratory, whether that's from, operational issues and operational perspectives or just, providing high-quality clinical care. And so ARUP has really spun up this Institute for Research and Innovation that kind of will allow us to really kind of push the boundaries as far as what tools like applied artificial intelligence can really provide for us. And so they were, I was lucky enough that they spun out a whole medical directorship for it. So we have, a whole group of us. David Ng runs the Applied Artificial Intelligence group over at ARUP, and I'm kind of his co-medical director. We have a group of about 6 or so software engineers and 6 data scientists. And, we've basically been tasked with, working a lot with kind of external companies and external partnerships to really build artificial intelligence solutions into their platforms or kind of solve issues with analytics-based solutions, be it AI or not. And then kind of look internally to see, what processes can we really kind of augment with AI, whether that's digital pathology and kind of on the anatomic side, or, within the core laboratories ourselves, what can we really do to, improve the day-to-day operations of the lab or improve, how our technologists are really interacting with the instruments or whether they should be at all interacting with the instruments. So it's really interesting grab bag of a lot of, there's no shortage of problems to be solved, and AI can potentially be a solution to a lot of them. So it's been cool that they've kind of formalized this position to really kind of explore what the high value targets are for AI in the clinical labs. And, I've been lucky enough to get that job. So it's been great.
That's awesome. And I recognize that you've been in the position now for a little over half a year, right?
Yeah.
So a lot of this is still new. But I'm curious, what are some of the most exciting things you've seen working in this area or exciting applications that you think would be worthy of sharing?
Yeah, that's a really great question. How much time do we have? I think, what's really cool about this job is that every day it's something different. We're building a lot of kind of generative AI models or working with these big foundation models for hematopathology or digital pathology. I think that'll have a pretty huge impact kind of on the grand scheme of things. But those are the like really big, like multi-year projects. I think the things that really kind of get me excited is that, we can come up with problems in our day-to-day medical directorship and just figure out solutions to them within, really short time periods, especially like once we get these infrastructures in place to start kind of implement these solutions. Like, a lot of our technologists are, interacting with, order comments that may or may not be particularly helpful for them, as they're trying to figure out what we need to do to a specimen and when. And so we can use, large language models or generative AI tools and agents, if you will, to really help them perform that task or really kind of extricate that somewhat redundant or mundane kind of burden on them so that they can really do the things that they like doing and enjoy doing about their jobs. So that's the kind of stuff that really excites me in the laboratory is how do we separate the kind of redundancy and low thought kind of monotony that the technologists might be experiencing and allow them, really free them up to, use that critical thinking and use that education that they've worked so hard to achieve into more interesting tasks. So, everybody comes to think of AI as being this big replacer of skill and talent within the laboratory. I'd be shocked if it ends up that way. I think, much like automation lines that we've seen so far, we build automation to make the rest of the jobs easier, but we're not really actually replacing any talent with this automation. Like FTE counts are staying the same, and we still need more and more technologists. So we're hoping at least that technologist retention will increase if we can make that job more fun to do and more interesting on the day-to-day part of it.
No, and that's an excellent comparison because we know with automation, what at least what we're seeing is yes, we still maintain the same FTs, but that's because the volume is getting larger. So it allows us to do more work essentially with the same resources. And as we all know, it's getting harder and harder to find qualified medical technologists to fill in these positions. So we naturally have to come up with ways where we can basically optimize efficiencies and increase our ability to do more. So I've been following obviously your work and seeing you've published a series of papers to make it concrete on specifically your work with IV contamination as one example of something you've been trying to solve using these types of tools. Can you talk a little bit about that? What it is, how big of a problem you found it, and what are some of the tools that you've experimented with that could help solve it?
Yeah, that's a great question. So pre-analytical errors in general are these errors that something is introduced to a specimen that happens before we even see it in the laboratory, and because it happens kind of outside of our walls, it's often really difficult for us to even detect that something has gone wrong. One really common type of pre-analytical error is this IV fluid contamination, which basically occurs, when a specimen is collected, if it's drawn directly from kind of an IV catheter that has some other substance flowing through it, or even just downstream of it, in a vein that's getting fluids from upstream. The patterns of kind of analytical errors that we see in those results that we're measuring can be pretty interesting. And, they can reflect not only the patient's physiology, but whatever that other substance is that's being introduced. So, for a good example, the classic one is if we're measuring glucose on a patient that's receiving a dextrose infusion, those glucose values can be through the roof, hundreds and hundreds of points higher than we would expect them to be. And while that example might be relatively easy to detect, with things like delta checks or just feasibility limits, a lot of these errors are somewhat more insidious and a lot more difficult for both delta check rules or anything that we're looking at from a univariate perspective to really catch both sensitively and specifically. So machine learning, really comes in here in that there are patterns of errors that are introduced to the entire panel of analytes that we're measuring whenever we have this kind of contamination event. And those patterns depend on what the fluid type is. So if we basically train a bunch of machine learning models to kind of be able to detect each of those fluids, we can combine them in interesting ways to be a lot more sensitive in how we say, this sample looks like it has some normal saline in it. It's probably about 10 to 20%, contaminated, versus the sample has lactated ringers or potassium EDTA, whatever it may be. If we use all of those analytes together and kind of detect patterns that we know should exist, it becomes a lot more sensitive and a lot more specific. So that, I think, really opens the door to a lot of these pre-analytical issues where, we have patterns that we know we should expect whenever one of these events occurs, but we don't really have good tools to really kind of empower us to take action on them in the clinical laboratory. I hope that machine learning becomes one of those tools, but we have a lot of steps between where we're at right now and really implementing machine learning in a useful kind of universal way for IV fluid contamination.
No, and that's an excellent point because in our lab today we use rules to detect these things, and sadly, it's more to say these are prone to operator error because not only they have to apply the rules, but also they have to know if you get a delta check what they have to interpret it and try to understand themselves. What is this because it was a wrong sample, or is this because it was IV contamination? What does it sound like? With this model, you're essentially standardizing the approach, and it doesn't require any input essentially from an operator, unless except to basically say, okay, qualify it as this type of error and move on and figure out what you need to do next. So I'm curious, this is a great example and like an example in the pre-analytical area for what you're doing inside the chemistry lab. I'm curious about other areas because obviously now you're overseeing more like this application in lab medicine. Do you have other examples that would be fun to share with our audience?
Yeah, I think it's a really great question. I think, machine learning has potential in pretty much every part of the laboratory. And so that's going to be a really fun process to kind of, as we move forward in time and we get, better at this task of iterating through problems and applying machine learning to them, what are the problems that really raise to the top as like high value targets? I think one that's particularly similar to the IV fluid in chemistry problem is that very same issue happens to every panel we do. CBCs are another, really high volume part of the laboratory. And the CBC, really guides treatment decisions in a very tangible way, especially, when we're talking about transfusions. We have a lot of rules as clinicians that say, as soon as the hemoglobin drops below 7, you should really be transfusing these patients. Even if they're below 8 and have some other comorbidities, you can think about it. And so what we basically sought to find is how frequently are these transfusions being given kind of erroneously because we're being really tricked into thinking that the hemoglobins are less than they are, either by contamination or some other source. One project that we were working with the folks over at WashU and Carly Macion for doing was detecting this kind of anomaly and resolution pattern in diluted CBCs and trying to figure out how frequently are these transfusions occurring after a contaminated CBC. And it turns out it's pretty scarily frequent. We're talking hundreds of transfusions a year are given, mostly for numbers that aren't believable.
Wow.
And trying to figure out ways. This brings up kind of an interesting approach in that this isn't just an isolated machine learning problem. This is a human factors problem and a machine learning problem. So can we build interesting clinical decision supports? Can we empower our technologists to have those often delicate, difficult conversations with clinical staff that says, hey, we have a bunch of numbers. I think they're diluted or contaminated. I can even kind of bolster that argument by saying this machine learning approach that's more sensitive than a human would be thinks this is contaminated. Can we check a point of care hematocrit before we give this bag of blood? Or, can we either cancel the results or report them as a comment and say, here are your numbers. I don't really believe them, but if you see something with the patient that makes sense in this scenario, treat them as you would otherwise, but don't just default to these being kind of a reflection of the real patient physiology.
No, absolutely, and it's important to highlight that, of course, this is happening everywhere. Just people don't know about it simply because of the complexity of the care we give and the total testing process, where things can go wrong that people delivering care may not be aware of because the person who drew the sample, if they've done it suboptimally, has caused this. So this is an incredibly important finding that would bolster the need for such applications to basically come in and say, this is inappropriate, do not treat and do not act on it. Right. So, I mean, between this and the pre-analytical example you've described for IV contamination, also on the chemistry side, how close are we to implementing any of these, and what are some of the barriers you see for implementation?
Yeah, that's a great question. I think a lot of it is going to be very kind of institutional specific, but even then, I would say that most, if not all, institutions are really just kind of trying to figure this out from square one. I don't want to say we're building the plane as we fly it, but we kind of are building the plane as we fly it. Pretty much every institution will have its own laboratory information system, probably a slew, dozens of middlewares that kind of allow us to interact with that data. Some will have really mature, kind of robust databasing systems to allow us to kind of do analytics retrospectively, but very few places are really kind of well positioned to build machine learning models directly into our clinical workflows at scale. And so I think kind of the biggest things here are building these interfaces. So right now we have LIS, we have middleware that kind of allows us to do whatever the LIS allows us to do, but very few of these kind of software solutions really allow us to interact with them in a kind of no holds barred situation where we can take information out, put information back in, build our own tests. There are going to be a lot of IT-based kind of barriers that we have to overcome, really to get to the point where we can start to solve machine learning problems purely by the machine learning. I think, the biggest one is interfacing. Like, can we get the data that we need in the times that we need it, and can we send stuff back? For the IV fluid contamination part, basically it's can we get all parts of the BMP out to our machine learning models, kind of out of whatever system it currently lives, and then send back those same 8 parts plus a prediction plus some comment that says, this is contaminated. We think it's contaminated because the sodium increased and the chloride increased and the calcium decreased. And can we do that in ways that are robust and at scale and, sound for clinical use? Because, we're talking about mission critical applications here that can't fail. And so it's one thing to build a bunch of cool machine learning solutions on a laptop, write a paper about it, and then move on with your life. It's a whole nother thing entirely to build them into clinical applications that have to be up 100% of the time. So
perfect segue to, you've spoken about the barriers from infrastructure. Given what you've just described, how's the regulatory space surrounding this work?
Yeah, that is a big question mark, I think, for now. Obviously, being laboratorians, we're no strangers to regulation. And I think, CLIA and CAP have provided sound skill sets for us to really start to think about AI in the same way we think about assays and tests. I think it'll be great if it ends up that way. But for now, we're in kind of this regulatory gray zone. Most machine learning models, especially kind of in the digital pathology world, will probably be considered medical devices and have their own, validation and implementation. Hurdles is probably the wrong word here, but body of evidence that you will need to submit to some regulatory body to kind of convince yourselves and others that you are doing something safe and doing it in the correct way. I think using CLIA as a model for that would be a great ending point for us. And Brian Jackson and a few others just recently wrote a really interesting kind of opinion article comparing the two and how we can think of AI in this CLIA-based framework. But for now, we're basically just trying to do the best we can to kind of convince ourselves that what we're doing is safe. And, most of what we're doing is on the operational sides of things, like helping us run our own laboratories, where the barrier to regulation really stops. Is it only clinical applications that need to be heavily regulated versus all the way out to, I am a clinical laboratory and I use AI to figure out staffing. Is that clinical? I think it's a fair question. And where you draw the lines, as well as what lines you draw, is for people much smarter than me to really figure out and help us kind of build these systems in a way that's, safe and effective for patients while kind of allowing us to innovate. So it's a big question. Hopefully we'll get more information here as far as how we should be doing this in the near future. But, for now, it's certainly a question that needs to be answered, but hasn't been.
And before we wrap up, I'm very curious, given that, again, you're one of the first few who I know who are working in kind of this role. Is there any advice you can give to people looking to enter the field, maybe trainees who are preparing, similar to you, who were still in training program, looking to prepare them for such a role? What advice basically would you give yourself in terms of preparation if you could 3-5 years ago?
Yeah, that's a great question. I think the biggest one, and it's maybe going to sound cliche, is just stay hungry. There is so much to learn and so much to know, especially in the data science machine learning world that's evolving so rapidly, that really, if you're not trying to stay on top of as much as you can and really staying hungry for that knowledge, you're gonna fall behind. That said, there are a lot of really great frameworks and really great sources for getting this information. Even YouTube and code academies or little coding certificates are great places to start. The informatics fellowships and informatics board certification will probably be a much bigger deal kind of moving forward in the future. But for now, there's just so much that you aren't ever going to get from a residency or a fellowship program that you're going to have to kind of learn on the job. And so keeping that open mind and, keeping this continuous improvement philosophy is, it's helped me a lot, I should say. I imagine it will help others kind of start to break into this space. There's definitely a hunger for it. Institutions are popping up these AI specialist jobs more and more, especially Path Outlines seems to have a new one every day. So it's been really fun. It's a really cool space to be in. We're kind of molding that space as we go. And, I'd be remiss if I didn't at least mention I'm, 8 months into this job. And so my thoughts on what are going to be important will probably change over time. But, I find it hard to believe that, having a hungry, like, continuously improvement philosophy won't be beneficial in the long term. As far as more actionable and more detailed advice, it might be a little up in the air for now.
No, absolutely appreciate that, and I will say that, especially given the amount of uncertainty you operate in, staying hungry and having that desire is very important to basically continue and push through. But thank you again so much for sharing your perspective, Dr. Nick Spies. Again, thank you for joining us. Thank you all for watching.
Thanks so much.